Let's see. Okay, so what are we going to talk about now? We have got to talk about friction. Chapter 8. Do you have any, I don't know, vague recollections from physics? Like, what do you think you know about friction? If you remember, maybe you're just popping something off and you're not even sure if you're right. What do you think you know?
I just remember it was like an opposing force. So like it only happened like it was mostly the box on the hill. So a box on the hill is like sliding down, and just the fact that it's sliding down means it has like an opposing friction force.
Yeah. So, put simply, and we actually saw this happen the other day in class, and you guys actually did some kind of creative things about it. But here's this table. Does it make sense? It's pretty resistant to me pulling on it. Like I got to kind of work to pull that. And of course, that's a combination of the bottom of this. It's got kind of rubber feet on the bottom of it, so that's kind of friction-ish. And if I remember right, Joseph was sitting on the table over there. We are going to pull on it. And one of Joseph, put paper underneath those because it's like you kind of realized intuitively that paper and rugs are slippery, and so it'll slip a little bit better in that situation. But the important thing is, what happens if somebody sits on this and then I try to do this? What's going to change? Anything? Way more friction. So friction is actually kind of proportional to the force that's on that. Now, right now it has its own weight. Maybe it's like 20 or 30 pounds or something, and so that's what's causing that friction. But if one of you 180ers jumps on this, you would probably want to be able to pull it down. And again, that's kind of what we saw the other day. That was kind of neat with the rope situation. Is maybe we're not able to pull that now thanks to the friction, but with the 3-to-1 advantage, where we're sort of tripling what our biceps could normally do, maybe I could actually pull this. And so one of the main things to understand is just when I try to pull this thing, notice I'm pulling it in this direction. It does what Connor said is true, which is friction is actually pulling in the opposite direction. I'm trying to pull it this way, and it's kind of saying no. Now, what's interesting though is there an arrow, if you will, in the 3-body diagram of this table? Is there an arrow down there pulling this way? The answer is no, because if it was, the table would be like going on the floor all by itself. It's more like a capacity. Does that make sense? In other words, if I walk up to it and I say, all right, I want to pull this thing, so I start pulling it, it's resisting that. It's like suddenly it's activated, if you will. So remember, if the forces aren't zero, the thing's moving. If the forces are zero, then it's not moving, and like, look, it's not moving right now. So it's like there's a friction component there, ready to resist anything I would do. Notice if I come up and decide to push it this direction, now all of a sudden the friction force is like resisting me in the other direction. But it's not like a permanent arrow where I can actually discover, oh, there's like 12 pounds of force going this way. Because if there was, again, the thing will just go sliding across the room all by itself. So that's kind of an interesting part of this and what makes it challenging. So the main equation that you've got to understand for this section that you would have seen, definitely would have seen something of. The friction force ultimately is, it turns out, proportionate. That's a really powerful word. Proportionate to the normal force. The normal just means perpendicular, and that's the person sitting on the desk. So if it weighs more, then it's just going to be harder to push across the floor. That's the idea. What does the basic simple equation typically look like? Force, I'll call it this, force, I can't remember the way your book says it, but the force of friction is equal to, and this is where proportionate comes in, is equal to the normal force. So it's proportionate to normal force, friction force, and normal force. What does it mean to be proportionate? It means those are equal, but you got to throw a constant in there. And that constant is typically, at least in this book, mu as a Greek letter. And that little s is for static. So this is like the static friction coefficient. So again, for the sterile book problems, they're just going to kind of tell us what that is. And by the way, this is something you can Google search on your phone really quickly. Like, what is the friction? We mentioned this a little bit on Thursday last week, but what is the friction coefficient between, say, rubber on the tire and asphalt? Like, that'd be an important one, right? Because that's the difference between crashing and not crashing. You probably all had the experience of driving on snow or ice at some point, and it's like, I don't really quite have the traction I usually have here. When I try to stop, I don't really stop now. I don't have the same good friction coefficient that I usually have. And so now all of a sudden I'm sliding down the road. But where does that come from? Well, you can actually look that up. That's something you could Google search for all kinds of kind of common things. But of course, there's things that aren't so common. Just really quickly, notice this calculator has some little rubber feet on the bottom of it. That's kind of a big deal. So that, and we will play with this in a little bit more detail later. But does it make sense that that should be sliding down the hill right now? If it was a ball, it would roll down the hill. If there was hardly any friction coefficient between these two things, this is pretty slick right here. But thanks to those rubber feet, there's actually a pretty good friction coefficient. There is now force. This thing does want to slide down the hill. There is now, if you will, an arrow going that direction with, say, 8 pounds of force. That's probably way too much, but 8 pounds of force. But there's also this friction arrow going the other direction that says, you haven't reached the level yet. Like, I'm not moving. At some point, though, I get this up high enough. At some point, there'll be enough force. And do you agree that there's more and more force the more I lift this? There's more and more desire for this thing to want to slide down the hill. Now, maybe you're surprised it hasn't moved yet. That's because of those rubber feet. But at some point, if I get high enough, the desire this has to go that direction, just like a skier sitting on a hill, is going to overcome the friction force that says don't go, and then this thing will start to slide. And notice it's still static friction because it hasn't moved. There is a force where it isn't called static and it's actually moving. Notice it still hasn't slid yet. When it does start to slide, it's probably going to crash and form brakes. So isn't that amazing? It hasn't slid yet. But what's going to happen if I tip this over this direction? Notice there's no rubber feet on it, in which case, like, it's already on its way. It's already sliding. But again, even here, it's like it doesn't want to slide yet because there is some friction, but it's plastic on plastic right now. And so that friction coefficient is going to be a lot smaller. And so by the time I get up in the air, it's like this thing's already moving. So friction coefficient is both weight, how much weight is this thing actually, but then also, how much slipperiness is there between those two surfaces. So having a good kind of conceptual understanding of that is important. Okay. So yeah, the way this kind of thing works in terms of something sterile, like a typical physics book, it's always some box on a desk or something boring like that. But if somebody comes up to this and pushes with, say, 100 pounds of force, that does not automatically mean it's going to move, because it depends on how heavy the box is. If the box is 5,000 pounds, it's probably not going to move if you push with 100 pounds of force on it. So I'm trying to get it to go that way. And its normal force, if this thing weighed, say, 130 pounds, then does it make sense that's its normal force? That's how badly that wants to go down into the ground, if you will. And so I have a force, I have a normal force, I have a force pushing on it, and I'm kind of wondering, is this thing going to slide? Well, the basic thing is, let's say that the static coefficient of friction is, I don't know, 0.2. So what this tells me then is force of friction. Well, where's the force of friction? If this is being pushed to the right, then the force of friction is always going to be opposing that. Does that make sense? Again, that totally changes if you suddenly grab it and say, well, now I'm going to pull it. Now all of a sudden it's going the other direction. So it's always trying to oppose that. Well, who's going to win here? This is kind of an equivalent of a tug of war. I've got 100 pounds pushing to the right. Well, what's that force of friction? We said that force of friction was equal to the static friction coefficient times the normal force, the weight of this thing pushing down perpendicular into the ground. 0.2 times 130, I think, is 26. So basically this has 26 pounds of capacity to resist that push. Notice the 100 wins. This thing is going to slide. Now, are you getting 100 pounds of push out of it? No, 26 is sort of being resisted. I mean, that wasn't easy for me to pull that across the carpet. And so in this case, it will actually slide.
So that 26 adding a little, it just seems kind of odd. That's such a small number.
Yeah, and that's basically because that 0.2 is a really tiny friction number. Like you're only sort of getting 20% of your 130 pounds because it's so slick. That was like plastic on plastic a second ago. 0.2 is not a very big number.
So if you're pushing with 30 pounds,
If you're pushing with 30, it's still going to slide, but it's not going to slide much because 30 is only barely bigger than 26. And so could I get this not to slide? Well, yeah, if I had a much larger friction coefficient, like between rubber and so forth, maybe that would be the case. Or what if I kept everything the same? Except for this box now does not weigh 130 pounds, it weighs 478 pounds. Now will it slide? Notice 0.2 times 478, maybe that's a bigger number than 100, maybe it's not. I mean, I just made this up, so I don't know. 478 times 0.2. Woo! 95.6. So the force of friction is able to handle 95.6 pounds. And so again, it's going to slide, but barely. Does that make sense? And you can imagine walking up to something and pushing it and going, oh, I can push it, but man, this is killing me and I'm barely getting it to move. And that's kind of the idea here. Okay. So to sort of ease into this a little bit, let's see if we can survive this first question that is up here. Did you all grab that? I saw some of you grab it, but not necessarily everybody. There's not too many good questions in the book, but this is actually one of them. Got so many cool things to show you. Actually, I want to show you something else first. I didn't make a copy of this, but this came straight out of the Ski Patrol magazine that we have to study to, and so maybe you've seen this if you've been up on the hill, but it's like since somebody eats crap and then they need to ride down the hill, they hop in that sled and then some skiers in front of them. But let's actually kind of figure this out. And this is kind of like the calculator on the table a second ago, in the sense that, well, it's the hill that's causing this whole assembly to want to slide. Now I've taken people before in sleds, and I was like, one of the times I was right below, I was kind of in the bottom of Dream, and I thought, oh, this is easy. I can handle this by myself. And so sometimes we'll have a tail roper on the back, like Plan B. Because you can appreciate if somebody's actually tied in that sled and you crash and then they just take off down the hill into the trees like that. It's not good. I would try to figure out how to disappear from the mountain if that happens. But I had a person on there and I thought, oh yeah, this is no problem. One of the cool things is we can increase the friction, and you can appreciate that sled in the back has a couple of rails on the bottom, skegs, and so it really wants to slide. But we can drop this chain that's in the front. It doesn't show here, but we can drop a chain underneath here. And the chain drags through the snow, which creates a ton of friction. And so in that way, it's like the brakes, if you will. But you got to also get where you're going at the bottom. And so I was like, I don't want too much brakes. So I'm like, I don't need the chain. And so the person hops in and I start skiing with them and I'm realizing I cannot, like, we're going and I'm not gonna stop this. Like, there's not enough friction right here. There's not enough friction right there for me to stop this thing. So it's just kind of a controlled free fall. I couldn't stop. Fortunately, I didn't lose it. I didn't crash and, you know, made the corner and died. But this is a bit terrifying. And so let's play with this a little bit. Notice this is on a 20-degree slope. And the person in the sled weighs 300 and the person who's a skier is 200. But what I'd like you to see if you can figure out is how much desire does that whole assembly have to go down the hill? All put together, that's like 500 pounds, right? And of course, the 300 pounds is the person plus, you know, the 30-pound toboggan or whatever it would be. Yeah, so you could think of it as just one 500-pound weight, or you could kind of do them individually. Just for the fun of it, I'm going to do them individually. But again, think vectors. What is this? If it's, you know, how much of that force is directed downhill? What desire does this have to slide? I mean, let's just kind of play with this for a second. I want you to think about that yourself. In the end, what you have is, and again, I don't think this is obvious. I don't think this is extremely easy by any means. Remember, 300 is the biggest number there is. Like, you're not going to get a bigger number than 300 for this person. And so part of their weight is actually going straight into the hill, perpendicular to it. And then part of it is actually going parallel downhill. Does it make sense? And you have to, I'm not going to take the time to jump here, but since the hill is at 20 degrees, in the end, that's actually going to cause that angle right there to also be 20 degrees. And so this creates this little right triangle. And so wouldn't this side right here be since 300 is actually the hypotenuse? And that's kind of my point, and that's what I think is not necessarily obvious. 300 is the hypotenuse of a triangle. It is not one of the sides. You're not going to get a bigger answer than 300. 300 is the maximum weight of this thing. So this would be 300 times the cosine of 20. Which is roughly 282. And this, of course, would be 300 times the sine of 20, which is roughly 103. My question to you is, what do those like mean? What is those, now that I basically converted this person's force into the two important directions here, notice one of them is into the hill perpendicular, and then the other one is parallel down the hill. What's the 103? What is that?
That's the normal force. Go down.
That's exactly right. This is its desire to go downhill. Notice it's not all 300 pounds. It's like a third of that. That's how badly that 300-pound toboggan and person combo wants to go downhill. Now, will that go downhill if it's all by itself?
But the 282 would be the friction.
Exactly. See, the 282 is not friction, but it's the normal force. It's the force straight into the hill. And that's what's so interesting. The 300 was not the normal force. That's why this is called the normal force. The 282 is straight into the hill. So whether this slides downhill is based entirely on how much friction do we get out of that 282. Now, if the bottom of that toboggan has rails on it and it's like a sled made to slide through the snow, then there's not going to be much friction resistance there. That 282 is not going to overcome 103. 103 is how badly it wants to slide downhill. Friction is saying, no, I'm not going to let you do that necessarily. there's always going to be some friction. Does that make sense? Even if it's just a tiny amount. And so let's just say, the coefficient of, and by the way, in this case, there's almost no friction at all, because that is, like I said, rails on the bottom, and pretty much it's going to go. The only real friction in this diagram comes from the skier's skis, tilted sideways, hopefully with good metal edges that are even filed to be, and that's your friction. Like if that doesn't overcome, you're doomed. Actually, so maybe let's continue this a little bit. So wouldn't the same thing happen over here? I'd have a certain amount of this skier's weight going perpendicular into the hill and certain going downhill. And again, this would be 20 degrees. And so this would be 200 times the cosine of 20. Which is 188 approximately. And this right here would be 200 times the sine of 20, which is approximately, I'll say 68. It's 68.4, but I just want to use round numbers. So would you agree that combined, that's, what is that, 171 pounds? There's basically 171 pounds of desire for this thing to slide downhill. If we said in the real world that there's basically no friction here, and when I said basically, that's impossible. There's always going to be some. But again, if that's a metal rail on snow and it's waxed and so forth, does it make sense the friction coefficient could be something like 0.02 or something ridiculous like that? That's kind of what you do with skis and snowboards, is wax them so that there's not as much friction there. So when I say basically no, maybe I'm saying it's irrelevant. I'll erase this, but what if it was something small, like say 0.03? If I multiplied that by the 282 pound normal force, 282 times 0.03, that's only 8 pounds. That's 8 pounds of resistance. How badly does this thing want to go downhill? Well, it wants to go down at 68 plus 103. That's how badly that wants to go downhill. Now, in the real world, as I said, this is the only place that friction really counts. And you can appreciate in that situation, if you turn your skis sideways and you dig them into the hill, that could be a really significant amount of friction. Let's just make something up. Let's say that friction coefficient was something really high, like, I don't know, 0.7 or something like that. Sort of 70%. What this means is you're going to get 70% of that. Well, since that only applies to the person's weight right there, because there's no friction back on the sled, like it wants to go down the hill, there's none back there. The skier is the only one. So if I take 188 times 0.7, basically I get 70% of that. I get a lot of it because there's so much friction. There's so much desire to slide there. 188 times 0.7 is 132. So if this is me, the skier holding the person in the sled, am I able to stop them? Notice they have 171 pounds combined of desire to go downhill. And this is the friction force that's pushing in the other direction. Who wins? The 171 wins. And so that's exactly what happened to me. Like I was trying to stop and I could not. I didn't have enough friction. And so I'm just going. Notice the net difference. If you take 171 minus 32, it's roughly 40 pounds. Fortunately, that's not so much that, maybe I still can ski and stay in control and nobody dies, which is what happened in my case. But that's kind of the issue. You're really kind of seeing who wins here. is the desire for something to slide, either because the boring example I gave a second ago, some box with an arrow just from nowhere pushing on it. But notice in this case, it's entirely because this whole assembly is up on a hill. There isn't any exterior forces that someone's pushing on anything. It's just that if you tip something on a hill, part of that breakdown wants to slide down the hill. That was this force here. And part of it is pushing into the hill. And the part that pushes into the hill is the part that friction makes a difference with. So again, I think this is just way more interesting than a typical, box on a ramp like you would see in a physics class. And it's even way more interesting than all the questions you're going to see in your assignment. But let's take a look at this now. So this is at least kind of a cool question because just to stare at it a minute, I actually want to give you a second to stare at it. This mine car is like full of rocks and stuff. And so it feels like, yeah, that's going to be really heavy. That's probably not good because it's not going to want to roll. And notice apparently the train that's hooked to the front of this or something. Again, typical book question, it's just some sterile arrow pulling from nowhere, but at least we can imagine it being a train, a car, an engine or something in front pulling on that thing. But notice that's a lot of force, kilonewtons. And I'm also glad that it's a force. It's in newtons, so I don't have to modify it. So let's see, what are they asking? Ultimately, the question is, does the car actually move? In other words, is that 10 kilonewtons of force going to overcome the friction force? Now, of course, I look at it and I think, well, those are wheels, like they like to roll, like there's not going to be a lot of friction there. Those are wheels. But did you notice in the problem that they said the wheels are locked? In other words, the brakes are on, so to speak. So let's just see if we can figure out what the heck is going on. So first of all, we're told that the car and its contents have a total mass of 6 mg. Again, are you getting good at this? What's mg? Megagrams. So that's actually 6 million grams. What do we not like about that number?
Yeah.
It's enormous, but it's not a force. Do you understand that? Because remember, force is mass times acceleration. So we have a mass here, but we don't have a force because it's still got to get multiplied by gravity. So let's see, I'm just kind of thinking out loud here. So again, this is a great sort of a tricky question. Excuse me. So the gravitational center of this, isn't it interesting? It's not in the middle. They're saying between the two wheels, it's 1.5, and the center of that would be at 0.75. So that could be because the ore is loaded more toward the back or something of that nature. But what are units? Like I need this to be newtons, right? Or maybe kilonewtons, but newtons. Remember, what's the unit for a newton? Kilogram meter per second squared. Oh, so I need that mass to be in kilograms, and they didn't give it to me in kilograms, but that actually means I don't need it in grams. Does it make sense to you that that would actually be 6,000 kilograms? And then I have to bring in the 9.81 meters per second squared myself. Now I have a force, and that will be in newtons. And maybe because the force on the chain is kilonewtons, maybe I need to think about that. But 6,000 times 9.81 is 58,860 newtons. So as I said, since this is in kilonewtons, maybe I want to think of that as 58.86 kilonewtons. I think I do. And I have to make them equal. So I could change 10 kilonewtons to 10,000 newtons and then just work it that way. But I'll call it 58.86 0.86 kilonewtons of force. Now, again, why am I interested in that particular number? I'm interested in that entirely because of the friction coefficient. Like that has nothing to do with whether this is going down the track. This is going down the track thanks to the arrow to the left that's trying to pull it down the track. That downward arrow is doing nothing other than telling us about friction. Does that make sense?
No, like it's giving us the radius of that wheel.
Yeah, what the heck? Why is it giving us the radius of the wheel? Why do we need to know that? That's not good. Now, does it make sense to you that we have, let's see, in terms of kind of creating a free body diagram of this, I've got the normal force at B, and I've also got the normal force at A, because I'm trying to add in all the arrows, right? That's the key to a free body diagram is what are all the arrows? I got the 10 kilonewtons pulling to the left. I got gravity now pulling down at roughly 59 kilonewtons. I've got the tracks pushing up on the wheels. And then because this thing is desiring to be pulled to the left, does it also make sense that I've got these two friction forces trying to resist this force of friction at A, trying to pull that direction. And then I've also got right here, the force of friction at B. And so now I actually think I have everything. I think I have all of them. So the bummer here is because this is not in the middle, because this isn't in the middle, I don't just get to split the 58.86 to each wheel evenly because it's not in the center. And so each wheel, the sum total of N of A plus N of B, the normal force at A and the normal force of B, that is going to be 58.86, but I just don't know that they're actually equal to each other. Again, if they're not, then the cart is sinking into the ground, right? Is it possible it weighs so much that the ground can't push back? But assuming this thing isn't moving up and down, assuming it's staying still at least vertically, does it make sense this statement has to be true for this to be, well, in equilibrium vertically? Good question. I haven't really thought about that. Vertical. Yeah, so let's see. It seems like there'd be 4 wheels. Did they say anything about that in here?
There was something like that on our last number.
They did say on the front wheels, plural, like there's 2 front wheels, and B, the rear wheels, they're plural. So they are giving me that hint. So that's a good point. So of course, I do need to think about that. So how do I figure out how much of the force goes to each location then? Or do I even care?
You care if it's 3-dimensional, right? Like if there's more gravel or whatever on the back left or front right, but it was 2-dimensional.
Yeah, it's like part of me thinks I don't care because the friction coefficient between each one is the same anyway. But again, this is illustrating what I said before. Looks like I'm not sure. I'm just trying to think. I'm just trying to figure things out. I don't know where I'm going with this. I'm not sure if I know exactly what I'm talking about. I'm just trying to figure stuff out. Remember that remember that one of the coolest calculations that is not obvious is the sum of the moments around something. And that's often what allows you to figure out how much is in each location. And again, I'm reminding you, I'm not even sure that I even care. Like, do I even need to know this? I don't know. But let's see, what if I figured out the sum of the moments around B? And so again, that would take out these 2 forces right here because they're pointing right at B, so they have no distance. And so the cart wants to rotate. Would you agree that because you are pulling on it over here, if this wheel was, if you will, sticky enough, does it make sense this back wheel could actually lift up off the ground? That's like one of the possibilities here. This could skid so well that the back wheel actually lifts up off the ground. I've got a cool problem I want to hopefully get to today that involves a mountain bike going down a hill and whether you go over the handlebars and stuff. I got a bunch of stories about that. And that's more interesting than this. But let's see. This thing's desire to rotate around B. Well, certainly this 10 kilonewton force wants this whole cart to rotate that way. We call that positive. And so I know it's 10 kilonewtons. I guess I'll leave kilonewtons in it. Oh, that's why they told me the wheels. How far is that away from B? It's 0.9 meters there and then another 0.15. So what is that, a total of 1.05 meters? So that's how badly it wants to rotate that direction. But then I've got this gravitational force that wants it to rotate the other direction around B. So that'd be negative. So 58.86 kilonewtons. And how far is that away from B? That's 0.6 meters away from B. And then notice I have two more force arrows over here. Do you agree that this one is actually lined up exactly with B, so that friction force isn't causing any desire to rotate because it's lined up, but this one will. This one wants it to rotate, assuming that's pushing on it. Then doesn't it want it to rotate that direction, which is also considered positive? So plus the normal force at A. And how far is it away? It's 1.5 meters away. And that whole assembly then should be equal to 0, assuming this thing actually isn't rotating. And I like that equation because it only has one unknown in it. I'm very happy with this equation. This is not like 323 we started the class with. Ooh, this is easy. So let's see, I'm going to move these to the other side and then divide by 1.5. So if I add 58.86 times 0.6, 58.86 times 0.6, and I subtract 10 times 1.005, 1.05 times 10, that'd just be 10.5. So I'm subtracting 10.5 to the other side. And then if I divide by 1.5, I'm getting 16. And since all of my forces were in kilonewtons, then I guess this would be in kilonewtons as well. And so now I could actually refer back to this equation up here. And since combined N of A and N of B have to equal that 58.86, then I could find N of A. So we're N of B. So I think I'll just kind of write it over here so it's sort of obvious what I did. So if this is 16.6, 16.54. So what is 58.86 minus 16.54? I'm getting 42.32. Whoa. So these aren't the answers. Again, this is my lingo. These aren't the answers to the questions necessarily, but those are kind of important numbers. Are you surprised that, I don't know, wheel B seems to be doing way more of the work? Like, okay, it wasn't 50-50, but it's like, isn't this pretty close to the middle? Like 1.5, half of that is 0.75. Isn't this pretty close to the middle? How come these are so far apart? Do you have a sense of that? What's causing that?
It's pulling at the top of the card.
Yeah, if this was just sitting here and it did not have this 10 Newton force on it, then they would actually be pretty close to each other. But remember what I said before, if this is pulling on this and this thing isn't moving, isn't this desiring to kind of go up in the air in the back? Doesn't this want to be lifted off of the ground? Well, that's taking away a bunch of that force. So a lot of the force that would have been back there had the cart was not being pulled on is taken away. So that's why A is so much smaller. So that's not as weird as it looks. Again, I'm totally floundering around right now because I don't know. Do I need to know? I figured out the split between the two. Do I care? Do I need to know? Do I need to know that? Now, remember what I am happy about is because I now know these two values. We said that friction force, these green calculations here, like those can now be calculated. Does that make sense? Because I know the normal force. So maybe I did need to know those. So when I'm told here that the static friction coefficient is 0.4, so I'm getting 40% of whatever the weight is.
Force is 10, right? So it's 10 plus, with that friction coefficient, would it be NA plus NB with the friction coefficient multiplied by both?
So yeah, you actually could put both of them together, but I will, since I maybe took the time to do this, I'll at least figure it out. What's the friction force at A? Well, that is equal to the normal force at A times mu of S. We just figured out that that normal force was 16.54, and we were told that this was 0.4. Yeah, so about 6.62. That's kilonewtons. And then the friction force at B is the normal at B times the static friction coefficient. Normal at B, we said, was 42.32. Friction coefficient was 0.4, 42.32 times 0.4 is 16.93. Now, again, I kind of forgot about the fact that there were 4 wheels till just now. What do I do about that?
Just divide NA and B by 1/2, splitting evenly between both wheels, and then you have to add the friction coefficient to all of them, right?
Yeah, I think maybe I don't have to do anything. Maybe this is like, so assuming this is kind of the front, since this is going this direction, then this is like the amount for both back wheels. Is that true? And this is for both front wheels. Maybe I don't need to do anything.
Yeah, you're right. So that doesn't make no sense.
Now, my gut reaction to this, again, I haven't totally read the question yet, but my gut reaction to this is this was getting pulled on this direction by 10 kilonewtons, and yet we have forces of friction of 16.9 and 6.6 kind of going the other direction. So my gut reaction is your engine's not big enough. Like there's so much friction force, it isn't able to slide. That's my first thought to this. Do you agree with that? Now, again, this is what's interesting about this. Notice those don't add up to 0. If you take negative 10 kilonewtons and positive 19 and positive 16.9 and positive 6.6, if you add those up, those don't add to 0. So does that mean it's going backwards? Remember, the force of friction is a capacity. So it's not like, that's not really there. It's a capacity. Basically, if you want this thing to move, and I add these together, since those add together to 23.5, then with the brakes on, you better pull harder than that or you're not going to move. Now, if you pull at 23, you might not know it, but you're just it's almost a slide. If you pulled at 5, you might not know it, but you're like, you're not even close. Like it's never going to move. You can try all you want, it's not going to move. You probably all tried to lift something that you couldn't lift or push something that you couldn't push. And you were kind of curious, like, am I close or am I not close? That's what's kind of cool about this calculation. So I don't know, have I answered the question? Now I'm going to go back and read it for the first time because I was just kind of figuring stuff out. Yeah, I think I did answer it. So the answer is nope, not even close. If you pulled with double the force of 10 kilonewtons, it's still not going to move.
Why is it when you get lower, you get more force? Like in football, they always say you get low.
That's because of moment. In other words, if you're really low and you have a lower lever arm distance, then it's much harder to kind of tip you over. But if you're really tall and you hit high, then you're going to get a lot more torque on you because your distance is so large. If you can get your center mass to be lower, then the distance is lower, and then therefore there's not going to be as much torque or desire for you to rotate.
I was thinking about like my like I want to put the maximum force like this shoulder.
As long as they're off balance, that's true. But if they're coming at you and it's like a fight now, like they run at you and you run at them, and you weigh more than they weigh, then you're probably going to win that battle and they're going to get knocked over. But if they lower themselves down, then you're going to lose because the amount of torque that you're generating is not going to be as much as they are.
That makes sense.
That's the gist of it. Okay. So 10 is less than 23.5, just to make sure this kind of looks like not moving. So what made this question, I think, a good question and interesting is the fact that, you had an engine pulling on it, something pulling on it. So let's now kind of switch gears to one other question, and then we'll be done for the day, which is this. And I don't have a copy of this. I didn't print this. Where is it? Oh, it's this. This is also a tremendously interesting and important question. I think we have kind of plenty of time to think about it. What I'd like you to see is this is kind of the same question, except for just like the skier and the toboggan a minute ago, what's causing the desire to move is the hill, not some external force. So there's like no external force here, but the fact that the bike is on a hill makes it want to slide down the hill. And so again, this is interesting to me personally because I ride mountain bikes a lot and I've been on stuff that was steep enough that I couldn't stop. If you full skid, I don't know how much you've ridden the bike, but if you full like lock the brakes up, you lose all your steering and you're in a steep section and that's not good. Like you need to be able to steer. And so from the biker's perspective, I'm trying to like keep enough brakes on that I'm keeping my speed down because I don't want to just let go and be like, oh, I want to steer. Well, if you let go very long, you're going like 50 miles an hour in the rocks and trees and you might get mutilated. So I'm like locking up the brakes, but I'm trying to like let off them a little bit so I can steer a little bit. And, if I'm lucky, I get out of that steep stuff before I fall in, and I can't believe I survived. But there's been many times where I'm on something that's so steep I can't stop. I mean, it's always a very good feeling if you decide this stinks, I want to stop, brakes, I stopped. Okay, danger over now. I can hop off my bike or whatever. But if you can't stop, not cool. So notice I tried to simplify this a ton. You have two different wheels that are both in contact with the ground, and you really have this 210 pounds. Now, what does that 210 pounds represent? Where's that coming from? Rider and bike. So bikes weigh around 30. So this would be like a 180-pound rider on a 30-pound bike. And notice I just kind of arbitrarily stuck the center of gravity to someplace. I wasn't really sure. But, it's some combination of where's the rider. I mean, I can kind of know about where your center of mass is, maybe about here. And that's a big part of mountain biking too. When you go down a hill, you actually want to try to get your butt off the seat and clear out over the back tire because you're trying to get your center of mass low. and back so that you don't go over the handlebars. So you might look at this and say, this looks pretty stable to me because the center of gravity is between the two tires. That seems like a good thing. So let's just kind of figure out what's going on here. Here's this person on this hill and they're sitting there. And notice I haven't given you any friction numbers and stuff. We'll just add that later on. But let's start with the very first thing, which is you have 210 pounds pushing down into the hill. And again, we're assuming that you're not sinking into the hill. So if that's the case, then just like in the last problem, we've got a normal force pushing back at that wheel. And we've got a normal force pushing back at this wheel. And it's not obvious, but why did I call those normal? Because that's a 90-degree angle. Those forces are not, the wheel is not able, there's no other way to put this in here. I don't know if this is obvious to you, but it's not to me. I could see somebody coming in here and saying, that's the force right there. That's how the dirt is pushing. But dirt can't push like that. It pushes at a 90-degree angle to whatever it's touching. Does that make sense? That's why it's called a normal force. In this case, because it's on a hill, that's not so obvious. A second ago, when the cart was flat on the tracks, it was kind of impossible to screw up because it was 90 degrees and straight up and down like I drew over here. But all of a sudden, when something is on a hill, it is important to understand the dirt can't do anything but push at a 90-degree angle. So again, I don't think that's obvious. So just like last time, I can actually figure out how much of that 210 pounds is the front of the wheel, A, handling, and how much is B handling. But notice in this case, it's kind of different because that 210 is pushing at a kind of at a weird angle. It's like some strange angle. So what do we do? Let's see, I'm trying to decide if I'm going to draw like an actual free body diagram. I do want to make sure you understand this. This is kind of interesting. Is it okay to actually call this the x-axis, even though it's like not flat? The answer is yes. And that actually could make our life easier here. I'm going to see if it does. And notice if I kind of rotate that to the ground, because effectively that's what I'm thinking of, is just kind of rotating that down until it's level. Does it make sense? This arrow up here is going to kind of rotate with that. So here it is up here somewhere, but now it's basically kind of pointing over in that direction somewhere. And that's 210. And just like I showed you with the skier a second ago, the important thing here is to break that thing up into how badly does it want to push into the ground and how badly does it want to kind of slide down the hill. Again, we're picturing this as not somebody who has the brakes off. If you have the brakes off, there's no friction and you basically are going to want to roll down the hill, but we have the brakes locked. And would you agree there's some kind of friction coefficient between a rubber, maybe a good high quality rubber knobby tire and dirt? But isn't there all kinds of dirt? Like there's dirt that's real sticky and maybe it's not muddy, but muddy enough that the, you know, all the knobs can like totally dig into the mud and you really might get a good friction coefficient as a result of that. But it also could be terrible because it could be like granite up behind my house where it's kind of like ball bearings and it doesn't want to stop you at all. Or maybe your tires are terrible and they're bald. So let's see. Well, if this angle is 32 degrees right here, again, it's no simple matter to work your way up to it, but can you picture that that would also mean that this angle is 32 degrees? So that means this side here would be 210 times the cosine of 32. Two ten times the cosine of 32, which is approximately 170. I'll call it 178.1. It'll be a little more accurate this time. So that's how badly this thing wants to go into the dirt, and it'll be NA and NB that sort of keep that from happening. They will be capable of resisting that. And this, of course, would be 210 times the sine of 32 degrees, which is 111.3. So your interpretation, your split here, just like we did with the skier a second ago, is to think this is sort of how bad bike wants to slide downhill. Again, I say slide because we are imagining the brakes are on. This person does not want to roll. They don't want to crash. And so this is how badly the bike wants to slide down the hill. That's a lot of pounds of force, but it's only half of 210. So again, it's actually cool, just like with the cart a second ago, that we can figure out how much is it A and how much is it B, how much of that 178 is at each of those two locations. And I can do that in the same way, which is with the sum of the moments around either A or B. I'll start with A. Sum of the moments around A. By the way, what's my free body diagram missing? This wants to slide down the hill. What's stopping it from sliding downhill? Yeah, I'm missing these friction forces. They're the opposite. They're going in the opposite direction. So the force of friction at B, force of friction at A. And so that's what's stopping it. That's the fight. Is 111 going to be bigger than force of A, force of friction at A, and force of friction at B, or is it going to be smaller? So some of the moments around A, well, I've got B pushing up. I've got the normal at B that I don't know times the distance those are apart, which is 5 feet. I'm going to leave the units off. I know my weights are in pounds and my distances are in feet. And see, do I have that right? Is that positive or negative? It wants to rotate that way. That's positive. Yeah, okay, so that'd be positive. But then I've got this force up here pushing down 178. That wants to go the other way, so that'd be negative. 178.1 pounds. How far is that away? I mean, isn't that this distance right here? How far is that away? Notice the whole thing is 5. It's 2 back here, so that means it would be 3. Remember, this is the advantage of turning this thing flat. I don't have to convert that. So that this distance right here is 3 feet. That's how far that 171 is. That 178.1 is. It's 3 feet away from A. Is that it? Equal to 0? Answer is no. What am I missing? That 111.3 is a force 2. So I'm not done. Technically, where is it? It's not so much down here where I have it drawn. It would actually be right there because they're emanating from that same point. So, you know, how far is that from A? What's that distance right there? Well, that's 4 feet. And that's causing it to try to rotate in that direction, which is positive. So that's actually a positive one. Now I can set all these equal to 0. And again, I'm very happy with that equation because there's only one unknown in it. So I feel like I can solve that, no problem. So if I add 178.1 times 3 to the other side, and I subtract 111.3 times 4 to the other side, and then I divide by 5, I get that the normal force at B is 17.8 pounds. And this is very interesting. I'll finish this part of it. Does it make sense if I look at this picture here? Don't I have, in terms of vertical, some of the forces in Y? I have 178 going down and N of B and N of A going up. So maybe I should write that out. I was going to be a little on the lazy side, but what are the sum of the forces in Y? And by the way, what am I calling Y? Since I rotated this so that this axis right here is my x-axis, then Y is going straight up. Over here in this picture, like this would be the y-axis. It's so much easier though if I just rotate it. I mean, I still want those to be 90-degree angles to each other, but to think of this, to rotate it as though this is on the ground, the only thing that changed is this force right here, which used to just be kind of going straight down, is now kind of going off to the side. But other than that, I didn't have to change anything. So the sum of the forces in Y, what do I have? I've got negative 178. And then I've got normal at A pushing up, and I've got normal at B pushing up, and that's got to be equal to 0. But I just got done figuring out that the normal at B is 17.8. Wow, look how big N of A is. Look at the split, how much each one was actually doing. 7.1. This produces the normal. The normal at A is 160.3. Isn't that crazy, the difference between these two? One is doing way more of the work. Again, why did that happen? It happened for the same thing that we just saw with that cart a second ago, which is because there was a force pulling downhill that actually put a ton of weight on the front tire, and it did exactly the same thing here. Now, super interesting. Just a little side note. What if I had done all this calculation and N of B had been negative? In other words, what's the dirt doing? It's pushing negatively. In other words, it's not actually pushing. Do you agree that in order for this bike to kind of not sink into the dirt, it was required that the normal at B pushed at, what do we say, 17.8? 17.8 pounds, that's barely pushing at all, but the dirt is pushing on it. You understand that? If that's the case, that means the tire is actually on the ground. Something's pushing on it. Had it been negative, that means you're going over the handlebars right now. Is it possible when you're going down the hill? Notice in the distribution of these two weights, almost all of the weight was on A. It is very possible, because I've went over the handlebars lots of times in this circumstance, it is very possible that N of A is some huge number and N of B is actually negative, and that means the whole thing is actually rotating. Is it possible? I'll take the time with our example tomorrow to show you this, but is it possible for this to be so sticky that when it finally tilted enough that it actually kind of did this and it actually tipped over? Does that make sense? Instead of slide, does it always have to slide? No, maybe it's sticky enough that it doesn't want to slide. when you get to a certain point, the center of mass is such that it starts to tilt forward. That's really easy to happen on a bike. It's not gonna happen with this calculator because the center of mass is so flat. But when I bring a box into class tomorrow, if I put rubber bands on it, it's very possible to tip it up and have the box just tip over. And that's when that force in the back actually turns out to be a negative number. So I've went face into the dirt many times when N of B in this calculation was actually a negative number. So bike tips over is the answer to that question.
Look at it with a shock in the front, make that as like a spring. Would that reduce the friction?
Not necessarily once the shock has done its work, but what the shock is going to do is change all these distances up here. In other words, I had 3, 2, 4, and 5 for these distances. So if the shock sinks in, then that's going to change kind of the moment calculations we just made a minute ago, because now those distances will be different. And that is a thing, because the front shock does end up taking a bunch of that weight. So super good observation. So let me just make something up and let's finish this and be done for the day. What if what I don't know what to pick here, but I'll say 0.62. I don't know where I'm getting that. I'm just making it up. That's a pretty big number. That means, you know, good tire tread, good dirt. And so what I'm hoping, of course, is this, that I'm not going to slide. So again, we just discovered that we're not tipping over. That's good. I didn't want to go tip over the bike and face first. So it's like, you know, I survived the first problem. The second one is, am I sliding in this circumstance? If I'm sliding, again, I don't like that because I'm out of control. I don't want to tip over. I don't want to be out of control. Can I actually brake myself to a stop? It feels like 0.62 is big enough that this is going to be okay. So just like we did a second ago, we can say, great, now I know that the force of friction in the A direction is equal to the normal force at A times mu. We just said this was 0.62. We just calculated that NA a second ago was 160.3. So if I multiply those, that's quite a bit of force. 160.3 times 0.62 is roughly 99.4. Force of friction at B. Normal at B times static force of friction. Again, this is 0.62, but the normal at B is a tiny number. It's only 17.8. So I'm not really going to get very much out of that. 17.8 times 0.62 is 11, roughly 11. 11.0 pounds. So the question, am I going to slide? Well, how badly did this want to go downhill? 111.3 is 111.3 bigger than or less than 99.4 plus 11.0? That's the question. Notice it's really close. It's like right on the edge. 99.4 plus 11 is 110. What's the answer? Am I sliding or am I not sliding? This one is bigger. So the desire to slide, desire to go downhill, frictional resistance frictional resistance? Answer, yes. Now, again, it's kind of cool that it's barely though. Do you understand that? So although I am sliding and I'm not able to stop, I'm not going to be going very fast. So I feel like, okay, I'm not going to die here. Not happy about it. Can't stop. But at least I'm not, at least the overall net effect is not a gigantic difference. This is only 1 pound off. So yes, but it's kind of qualified by barely. Won't take the time to calculate this, but maybe this makes sense to you. If you moved your center of mass, so here it is, here's your center of mass right here, and I gave you these 3, 2, and 4 distances. Does it make sense if you moved your body forward, which your body is a huge part of that 210 pounds? If you moved it forward, does it make sense that this normal force back here might be negative? And that's like what would cause you to go over the handlebars? Can you see that actually happen? Can you see how the calculation would work? If that was the case, my guess is if I switched this to 3 and this to 2, by sliding the center of mass up to here, my guess is that probably would come out negative, and I would be tipping over.
Even if you set it to 0 like we do, because we're saying it's not going to rotate, right? When we set moment around 8, 0, so no matter what, it's not going to come out negative, is it?
So no, it can ultimately rotate, because in the end, if that, yeah, I mean, we set it equal to 0, saying we're assuming it's not rotating, but the answer could be, well, sorry, it is. It is rotating, because ultimately, if this number is negative, that does not mean there's like some force pulling down on it. It just means it's not touching the ground anymore.
What would it look like if you were sinking like a quicksand?
If you're what?
Like sinking in quicksand?
Yeah, I mean,
What would
that's,
that number be?
and the fact that we were able to say the sum of the forces, where do we do that calculation? The sum of the forces in y is equal to 0 is because we're saying, well, the dirt is able to do a job here. Is it possible the dirt can't push up like that because you're in quicksand? Yep, totally is. And the bike just slowly sinks down. So yeah, but you're able to assume, obviously, in the case of most cars on roads and so forth, that it is able to resist that. Interesting. Okay, let's shut up for today. So what I want to do is just add realism to this on Thursday and spend a huge chunk of our time kind of trying to like slide a box on a table. And I'm going to bring, I've got an app on my phone that tells you what angle something is at. So when we tilt the table up, like a second ago, the dirt was at 32 degrees. Well, how are we going to know that? If that table's tipped up? Well, I've got an app on my phone that'll tell us what that angle is. And when it starts to slide, we're actually going to be able to calculate the coefficient of friction, like actually figure out what that number actually is, which is kind of cool to be able to do. All right, I need to show up. As always, stay after if you like.